In this video, we talk about finding the area of a region between the graphs of two polar equations. In order to do that, we're going to have to find points of intersection of the graphs of polar equations. I'll tell you some things to watch out for there. And then we'll look at our graphs and we'll use what we're looking at. We'll use what we see to infer the formulas for area. So here's our question. Let's say somebody asks you to find the area of the common interior between the graph of the polar equation given by this function and then r equals 2. Well, the way you want to always start these problems is you want to graph the two functions. R equals 2 is pretty simple. It doesn't matter what theta is, r is always equal to 2. So we'll graph that. I've actually already graphed that for us. Just a circle of radius 2. Centered at the origin. And this one, r equals 4 sine of 2 theta, we can graph using the same method that we talked about in earlier videos. So let's graph that function. And the way we do that first is we graph r versus theta. So that's sinusoidal function. Just looks like this. Now, instead of the amplitude being 1, like it typically is, we've multiplied this sine function by 4. So we go from -4 to 4. And the period for this function is 2 pi divided by the coefficient of theta. So 2 pi over k in general. This time k is 2. So the period is pi. All the interesting things happen at 1/4 of the period. So that's half of pi, that's 1/4 of pi, oops, that's 3/4 of pi. We've got this curve. And now with this curve in this equation, we can come up with a table of values. Now to come up with my table of values, I always like to use an increment of the period divided by 8. So we'll do that. So I've got, let's look at all those interesting things that happen at 1/4 of the period first. So we'll have 0, pi over 4, pi over 2, 3 pi over 4, and pi. And we start at 0, then we go up to the max. Then we go back down to 0, then we go to the min, which is -4, and then back to 0. And then at these other points, that's pi over 8 and 3 pi over 8, 5 pi over 8, and 7 pi over 8. Well, if I replace theta with pi over 8 here, this angle becomes pi over 4, or equivalently 45 degrees. So this is 4 times sine of 45 degrees, or 4 times square root of 2 over 2. So this simplifies to 2 root 2, which is about 2.8. And then by symmetry, that's going to be the same value. It's about 2.8. This is the same, but it has opposite signs. So that's -2.8. It's -2 root 2 if I want to be exact. And this is -2.8 as well. Okay, so now I have this table of values, and it will allow me to sketch this curve. So what do I do first? I sketch this curve, I find the increment, I make a table, and now that I have my table, I go over here and start sketching. Oh, actually, before I do that, I want to do one more thing. Since we're trying to find the area of the common interior between this function and this function, I'd like to figure out the values of theta where these guys are equal to each other. It'll make my graph a little bit more precise. I want to use these values on my graph, but I'd also like to have the exact values of the points of intersection of this curve with this curve. Now, the way we find the points of intersection is we set the r on this equation equal to the r on that equation. Just like when we do in algebra class, we set the y's equal to each other and solve for x. Similarly, we're going to set the r's equal to each other and solve for theta. Now, sometimes this doesn't work. Sometimes there are points of intersection that aren't a solution of this equation. So we'll find the solutions of this equation first, and then we'll look at our picture when we're done, and we'll see if there are any that are missing. So I'll divide both sides by 4, and I get sine of 2 theta is equal to 1/2. So I will solve this on the interval where 2 theta is between 0 and 2 pi. And sine is positive in quadrants 1 and 2. Sine's positive where y is positive. So these are not to scale. Opposite over hypotenuse is 1/2 for both of these. Opposite over hypotenuse is 1/2. And I see right away that these are 1, 2 square root of 3 triangles. So I say not to scale. The dimensions are sort of flipped, aren't they? The angle opposite the 1 in that triangle, that has to be our angle 2 theta that we're looking for. Well, this angle in a 1, 2 square root of 3 triangle is the 30-degree angle, or the pi over 6 radians. So then I can divide both sides by 2, and I get theta equals pi over 12, which is 15 degrees. And then over here, this 2 theta is equal, or this 2 theta over here corresponds to, or this reference angle of 2 theta over here corresponds to this angle. Well, this is 30 degrees, so this is 150, or if this is pi over 6 radians, this is 5 pi over 6. And then we divide both sides by 2, and we get 5 pi over 12, which is 75 degrees. Okay, so that's great. I know that this circle meets this curve when theta equals 15 degrees and when theta equals 75 degrees. And if we want to find the r value, well, actually, we already know the r value. The r value is 2. So the points of intersection are given by 2 and 15 degrees, or 2 and pi over 12 radians, or 2 and 75 degrees, or 2 and 5 pi over 12 radians. Okay, now there may be other points of intersection, but we'll find out a little bit. We'll find out more when we graph r equals 4 sine of 2 theta. Now, if r1 wasn't equal to 2, then I would have to replace theta with pi over 12 here and replace theta with 5 pi over 12, and then I would see what the r values are at these theta values. But because r equals 2 on the other one, I know that r will equal 2 for this one as well. So those are 2 points of intersection. That's going to be helpful to us. So we know at 15 degrees and at 75 degrees, that's pi over 12 and 5 pi over 12 radians. Our curve will meet here and here with this other curve. Okay, so those are 2 points on this graph. All right, now let's plot the rest of the points. When theta is 0, r is 0. When theta is pi over 8, and that's half of 45 degrees, so 22.5 degrees, theta, or r, is 2.8. So here's 15 degrees, there's 30, 22.5 degrees is about halfway in between, and I want to go out 2.8 units from the origin there. Right here, so I go out 1 unit from the origin, 2 units from the origin, that's 3, that's 2.75. So I want to go out to about 2.8. So maybe there, approximately. Okay. And then at pi over 4 radians, that's 45 degrees, r is equal to 4. And r equals 4 is right out here. So we'll plot that point. And then at 3 pi over 8, so that's 45 plus that 22.5, so 67.5 degrees. R is 2.8 again. So there's 2.75 and 2.8 is approximately there. And then at pi over 2, r is 0. And so we're back here. So I think we can see from this that our curve roughly looks like this. I don't know if you can tell, but our curve was given by r equals 4 times sine of 2 theta. So this is a rose curve. Whenever n is even, you have a sign, and this is an even number. You get petals. You get twice as many petals as the number that's there. So if n is 2, we're going to have 2 n petals. So we'd actually have 4 of these. We get 1 in this quadrant, 1 in this quadrant, 1 in this quadrant, and 1 in this quadrant. But remember what we're looking for. We're looking for the area of the common interior of those 4 petals, and r equals 2. So what I'm really looking for is this area here. But times 4, because there are going to be 4 petals. So we'll have 1 in this quadrant, then 1 there, 1 there, and 1 there. So I want this area. Okay. So I think we can see what we have to do. We just need to identify which function's on the outside. We need to find the angles that go with each function being on the outside. Okay, this is what we've got. I want to find the area of this region times 4. So there are going to be 4 of them because it's a rose curve with 4 petals. Okay, now we said earlier we had points of intersection over here at pi over 12 and over here at 5 pi over 12. But be careful. That line, theta equals pi over 12, looks like that. Oops. It looks like that, super straight. And the line theta equals 5 pi over 12 looks like this. So if I integrate from pi over 12 to 5 pi over 12, I'm going to get this area right here, but I'm going to be wrong. I'm going to miss part of the area. There's a little piece of area that goes right here and right here. So we're going to have to find that area, and that area, and then we'll add them all together. Okay, that's the plan. We've got our picture, and notice that the points of intersection we had 2 points of intersection, excuse me, at pi over 12 and 5 pi over 12, which is exactly what I would expect. And then because of symmetry, we can multiply that area by 4. Okay. Now, if I looked at my graph and I saw a 3rd point of intersection, I would have to be very careful as I go through tracing out these graphs as theta increases. And I would have to think about the location or the value of theta that got me to a particular location in order to infer the bounds for my graph in that case. So we have to be very careful, but most of the time, or often, we can just set the r's equal to each other, and that's going to find us at least some of the points of intersection. We just might miss some. Okay. So what do we need? Well, we need the area of this innermost region first. That's probably going to be the easiest because it's bounded by a circle of radius 2 and 2 lines for theta. Theta goes from pi over 12 to 5 pi over 12. So our area is equal to the integral from 5 pi over 12, excuse me, to 5 pi over 12 of 1/2 of r of theta squared with respect to theta. But we're just on that circle of radius 2, so this is really simple. So half of 4 is, of course, 2. An antiderivative of 2 with respect to theta is 2 times theta. And we get this. We have 2 times 5 pi over 12. This is actually a fourth of the whole total area. Minus pi over 12. That's 4 pi over 12, which is the same as pi over 3, times 2. So that's 2 pi over 3. Okay. Now the next part is this area here. Now this area is bounded by the equation of this rose petal in our rose curve. So the r value here is r equals 4 sine of 2 theta. Now theta is starting at 0 and going out to pi over 12 to trace that part of the curve. So we've got an integral from theta equals 0 to pi over 12 of the equation of that rose curve to find that area there. And then we'll do the same thing from 5 pi over 12 to 90 degrees, which is pi over 2 radians, to get that area over there. Now I'm pretty sure by symmetry that area is going to be equal to that area, but let's verify it by doing the calculations. Okay. So I have the integral from 0 to pi over 12 of 1/2 of r squared d theta plus the integral from 5 pi over 12 to pi over 2 of 1/2 of r squared d theta. And this time, we're on that rose curve, so r is equal to 4 times sine of 2 theta. 4 squared is 16, half of 16 is 8. And if I want to anti-differentiate sine squared of an angle, if there's no cosine squared of the same angle, I've got to use a power reducing formula. So power reducing formula for this is 1/2 of 1 minus cosine of double the angle. So that angle is 2 theta, the new angle will be 4 theta. That 1/2 times that 8 is going to give me a 4. So I've got 4 times the integral of this. The antiderivative of 1 is theta. The antiderivative of cosine of 4 theta is sine of 4 theta. We'll divide by 4. And then we'll substitute 0 and pi over 12 and subtract. So we've got 4 times pi over 12 minus 1/4 sine of pi over 12 times 4, so that's pi over 3. And then at 0, we have 0 minus sine of 0, which is 0. So we just get 0 there. Okay, so that's part of our answer. And that's part of our 1/4 of the total area that we're looking for. And this is the same function as this, so it's going to have the same antiderivative. So let's just write down that antiderivative again. I'll distribute my 4 this time. I've got 4 theta minus sine of 4 theta. We want to integrate from 5 pi over 12 to pi over 2. So substitute in those bounds and we'll subtract. Okay, so let's see what we've got. I've got 1/4 of the area is 2 pi over 3. And then if I distribute, it should be a pi over 12. This 4 here, 4 times pi over 12 is pi over 3. And then I'm subtracting sine of pi over 3, which I'll leave alone for right now. We'll simplify that in a little bit. And then over here, we're evaluating this expression at pi over 2 first. Pi over 2 times 4 is going to be 4 pi over 2, which is 2 pi. And then we're subtracting sine of 4 times pi over 2, the sine of 2 pi. We know that's 0. So that's evaluated at the upper bound. And then we want to evaluate the same expression at the lower bound and subtract. So I substitute in 5 pi over 12 for theta, multiply by 4, I get 5 pi over 3. And then I've got minus sine of 5 pi over 3 there. Yep, that's what I want. Okay, so this is our answer. It's just not simplified. Or actually, it's not our answer. We multiply both sides by 4, and that's going to be our answer. Let's see what we get. Okay, I've got sine of pi over 3. In order to evaluate that, I'll just draw a triangle over here. That angle is pi over 3 radians, or 60 degrees. So that's a 1, 2 square root of 3 triangle, and the side opposite the 60 is square root of 3. So this sine of pi over 3 is opposite over hypotenuse, square root of 3 over 2. Okay, and sine of 5 pi over 3, that's the same reference angle. The only difference is we're in quadrant 4, so sine is negative. So this is negative square root of 3 over 2. Okay, so I've got this plus this is pi, minus root 3 over 2, plus 2 pi, minus 5 pi over 3. And then I'm subtracting a negative times a negative. So that's a positive times a negative is going to be negative ultimately, because we've got those 3 negatives multiplying each other. And that's square root of 3 over 2. Okay, so this is 2 pi minus 5 pi over 3 is going to be pi over 3. And I've got pi over 3 plus pi is 4 pi over 3. And this negative square root of 3 over 2 minus that one, it's going to be negative 2 root 3 over 2, which is just root 3. That's 1/4 of the area. In other words, it's that area right there. This area right here turned out to be, according to our calculations, 2 pi over 3. And this area, according to our calculations, was pi over 3 minus root 3 over 2. And if we simplify this, we end up finding that this is pi over 3 minus root 3 over 2 as well. So this area here is equal to this area here, which is what we thought, right? Because it's symmetric. So when we simplify, we get this, and then the area for all 4 of the petals that I didn't draw because it takes a long time, and they would be more symmetric than that. I've got a circle, of radius 2. Yeah, so this is why we tend to use computers for this. That area is this times 4. You don't have to, but if you want to, you could factor out a 1/3. And that would work as long as you multiplied that one by 3. If you distribute, You'll get that. Okay, so that's the area. Now let's go over what we just did. Okay, so somebody asks you to find the area of a region between two curves. You have to graph the curves. And one of the things that you'll need to do is you'll need to find the points of intersection of those graphs. Now, one way that you can find the points of intersection, or at least some of the points of intersection, is by doing this. You set the R values on one curve equal to the R values on the other, and then you just solve this equation. I just solve it on the interval from 0 to 2 pi, where my angle is between 0 and 2 pi. And then I just imagine what happens to that as theta increases through all the values. So that gave me the values on the interval where 2 theta was between 0 and 180, which meant theta was between 0 and 90. So that's good, because that means my only points of intersection are here and here. And when I graphed this curve and I graphed this curve and I saw that I had 2 points of intersection, and that was consistent with what I did already when I did earlier, and I found these 2 points of intersection, then I knew that there was no more work to do. And if there was some third point of intersection, we might have more work to do. And then we said, okay, now that I've got this picture, I need to find this area. And basically the way we found this area was we found bounds for theta for this region, and we found the right value of R for this region, which happened to be 2. And then we said, notice that part of that petal goes outside of the lines pi over 12 and 5 pi over 12. Part of it is over here and part of it is over here. So to get that little bit of area, we have to think about where theta starts and where theta stops to get this little piece of this rose curve. Well, theta goes from 0 to pi over 12 to get that piece. I don't actually know the values of theta that correspond to all of those points, but there are values of theta between 0 and pi over 12 that correspond to those points. So we wanted to integrate this curve between 0 and pi over 12 to get that area. And then we integrate the same curve between 5 pi over 12, which is given the equation of this line, and pi over 2 to get that area. Now you could have just doubled this area and said by symmetry that's going to be equal to that, and then add that area. That's fine, but I wanted to confirm it geometrically, or not geometrically, wanted to confirm it by evaluating the integrals, and it turns out the integral of this piece is equal to the integral of this piece, so it is symmetric like we thought. And then you just take those 3 areas and you add them together. So it's just this area plus this area plus this area. Now I will tell you, when you're graphing these by hand, sometimes it's hard to tell that that curve goes just a little bit beyond. So you might want to use something like Desmos.com to graph these. If I ask you to graph something like this, I will probably give you the graph so that you can see it. If I ask you to graph something like this on a test, I will show this to you, but you'll still have to find the points of intersection. And you'd still have to draw in those lines yourself. So make sure you keep that in mind. If one curve goes beyond that line for theta, you're going to end up with a separate integral for that piece, and a separate integral for this piece, and a separate integral for that piece, integral for that piece. But again, I will give these graphs to you, or it'll be something very simple like a circle, or like the rose petal that we found in the last video, whose area we found in the last video. Okay, so you sketch them and you look at the picture, and then you set up the area integrals for each of the parts, and that is how we find the area between 2 graphs given by polar equations.